This video is going to cover section 12.1, the counting principle. Okay, so we're moving into something called combinatorics, and we'll also see permutations in a few sessions later. Okay, so we're going to go ahead and start by talking about basic counting by making a list and talking about what combinatorics is. So here you have that combinatorics right here. Okay, is the study of counting the different outcomes of some task. So, for instance, if we flip a coin and we want to know if it's heads or tail, that has two outcomes. It's either going to be heads or it's going to be tail. Okay, and that would be your sample space for this particular problem. Another example is if we have a regular die, a six-sided die, we have that we can have 1, 2, 3, 4, 5, 6. Any of those faces can appear, and that would be listed as such 1, 2, 3, 4, 5, 6, which means there are 6 possible outcomes. Okay, so this is what we're kind of dealing with here. We have a few definitions down here. We have that an experiment is an activity with an observable outcome. So the studies we're going to be looking at here are experiments, and we can if we were to try them, they would have outcomes that we could actually observe. Definition two, the sample space, which I kind of mentioned, is the set of all possible outcomes. So this right here would be a sample space. This would be a sample space. Okay. And finally, third definition, an event is one or more of the possible outcomes of an experiment. So the event that if I flip a coin that it gets heads, that's one of the events. Tails is another event. Each of these is another event for the the die problem. Okay, so let's go ahead and go right into an example and see how this works. We have example in 1 and 2, so these two, list the elements of the sample space defined by each experiment. So these are kind of simple, just to kind of start us off. We have that for number 1, select an even single digit whole number. So when we're talking about whole numbers, we're talking about the ones from 0 through 9, okay? So in this case, that would be, let's see, so for number 1, okay, we would have even numbers, so 0 to, actually no, 0 wouldn't count, so it would just be 2, my bad. So 2, 4, 6, 8, and that's it because they want it to be a single digit, so if I go past that, it's already a double digit. Okay, so that's it for number 1. For number 2, let's select an odd single digit now. So now we're doing the other ones. We're doing, let's see, 1, 3, 5, 7, and 9. And again, we're not going to go past that because once you go on to 11, that's already going to be a double digit, and we just want single digits. And that's it. These would be your answers for these two problems. Okay, pretty easy stuff. So let's go ahead and look at a few more definitions now. We have, ignore the bottom for now. We have it a single stage experiment is an experiment for which there is a single outcome. So the ones we did right now, if you flip a coin, you get one outcome. It's either heads or it's either tails, okay? So those are the ones that are usually a little bit easier to deal with. A multi-stage experiment has 2, 3, or more stages. So this one can have more than one. And here's an example to kind of show you what we're referring to in that sense. If you consider a two-stage experiment of rolling 2 dice, okay, so you're going to have 2 dice. One of them is green and the other one is red. Okay, how many different possibilities, how many possible outcomes are there? So one way to do this, and this is also in your book, is to make a table. So this method right here is using a table. And what the table does is it lists all the possibilities of one. So this would be like the green possibility on the side here. I'm going to scroll up a bit. So this would be all of the green outcomes we have. It could land on 1, it could land on 2, could land on 3, and so forth. So it has 1 through 6 on this side. And then they went ahead and did the red ones on the other side. And it's the same thing. It can land on 1, 2, 3, 4, 5, 6. And what we're doing is we're combining each one to give us the sample space. So this entire thing right here, so that I'm kind of outlining in blue, okay? These are all the possibilities of how we could get this. We could get them both. Let me use a different color. It's kind of hard to see. We can get them both to land on a 1. We can get one of them to land on 1 and one of them to land on 2. You can kind of see they just kind of match up like this. So like for instance, this one would be the green one is 2 and the red one is 3 and so forth. So you can see that we have, let's see, how many do we have? We have 1, 2, 3, 4, 5, 6 across and then 1, 2, 3, 4, 5, 6 down. So it looks like we have 36 possible outcomes. And that would be the answer to the question that I asked at the top. Okay. Now, what if I asked a more targeted question and said, well, how many of these outcomes would add up to 5 or something like that? Well, you could go and say, well, let me see, I have an outcome of 5 right here, where the green dice is 3 and the red one is 2, and that would be one possible outcome. And I would look for the other one where this one is 3 and this one is 2. So that would be this one right here. So you could add questions onto these type of scenarios. But in this case, I just wanted to show you how we would construct a table. Okay, so this is one method that you could use to count the possible outcomes. Let's look at another one. How many ways can you answer the first 3 problems on a true or false quiz? So now we're thinking about a quiz and we're only looking at the first 3 problems, okay? So this method is called a tree diagram, and I'm sure you've seen it at some point, okay? And let me explain this, then I'll kind of talk about a different example that you might have seen in the past. So for question 1, since it's true or false, question 1 can be either true or it can be false. Okay, so what you do is from this outcome, you branch off and say, well, what could the next possible outcome be? So for question 2, well, again, question 2 can be true or false also, but we have to include it on both of them because if question 1 was false, then you can still have this combination over here. And then we move on to question 3. Question 3, well, it can be true or false also. So we branch off true or false for all of the combinations we have so far. And then in the end, this is what you end up with at the end. True, 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 that's one possibility. True, true, false, that's another possibility. True, false, true, and so forth. And you can see from our list that we have 8 possible outcomes. Okay, and this is just for the first 3 questions on a true or false quiz. So if it's not that many things you have to do, you could use a tree diagram, okay? Another popular example you might have seen is they might say you have a choice of, an appetizer, an entree, and dessert. How many possible outcomes do you have? So you would list, well, I can get, the spinach and artichoke, and then the chicken, and then cheesecake. Or I could do spinach, artichoke, chicken, and chocolate cake, and that would be 2 different outcomes. Okay, and this one is pretty popular. The tree diagram is pretty popular for those kind of things. But what if I wanted to know how many ways it'd be for all 10 questions? So you see how with this one, you would have to make a really big tree diagram, okay? So this is where what we're going to be addressing actually for the rest of the video, something called the counting principle that makes this whole thing way easier, hopefully way easier, and you don't have to draw so many pictures. If you want to keep on drawing the pictures, so by all means, if you have the time, go ahead. Okay, so we're going to go ahead and move on to what this unit is actually about, the counting principle. Okay, so here we have 2 of the examples, okay, that we previously already went over. We have the one with the dice. So this was the one where you rolled the dice. You had the green dice and the red one. And you said how many different possibilities do we have? Okay, so well, for the red one, you know that it can land from 1 through 6. So that was 6 possibilities. For the green one, same thing, 6 possibilities, and 6 times 6 gives us 36, which we saw in the picture in the table. That is actually correct. So what the counting principle does, instead of making us do all that work, is it calculates all the number of possible outcomes. So we calculate all the number of possible outcomes without listing. And by doing this, we find the product of those possible outcomes. So you say, well, for this instance, I can do this many times, and this one can happen this many times. If I multiply them, that gives me the total number of possible outcomes I have. Okay, something like that. If we look at the question about the test, okay, now we just wanted the first three questions. We know that for question one, okay, there's two possibilities. It's either true or false. Yes. For question two, well, now we have four possibilities, but again, there's only two. Hang on, let me do it this way. For question two, they can there's four possibilities here, but each of those only has two also. So in other words, question one can either be true or false. That's why we have two. Question two can either be true or false. That's why we have two. Question three again can also be either true or false, which is why we have two. And if you multiply two times two times two, we get eight. To be more specific, this one could also be 2 to the third power, which is 8. And with that information, the question I asked before, what if we wanted all 10 questions? So if I wanted all, let's say the quiz had 10 questions, okay, for this problem. Well, I would say, well, it's going to be 2 for the first one, 2 for the second, 2 for the third, 2 for the fourth, and so forth till we get to the 10th. So it would be 2 to the 10th power. Okay. Interesting. A lot easier than doing all this as well. So what we're going to do is we're going to go ahead and define this officially now. Okay. The counting principle. The counting principle says the following. Let E be a multi-stage experiment. Okay, so that's kind of like our stage here. If N1, N2, N3, all the way to N sub K are the number of possible outcomes of each of the K stages, so like think of the stages like the question 1, question 2, question 3, okay? Then there are n1s times n sub 2 times n sub 3 all the way to n sub k possible outcomes. So in other words, for each stage, we have this many possibilities times this many possibilities for the next one. And you can see here that multiplication, okay, going on between all the way till you get to the last one. So let's go ahead and do an example with this now. We have in horse racing, a trifecta consists of choosing the exact order of the first three horses. Okay, across the finish line. If there are 8 horses in a race, how many trifectas are possible? So we want to do a combination of 3, assuming there are no ties. So let's see. For horse number 1, so for the first place horse, we have how many horses do we have to choose from? Well, we have 8 horses to choose from. So out of those 8 horses, one of them is going to get first place. Okay. For second place, how many horses do I have left to choose from? Well, one of them already got first place. That means I only have 7 left. We're going to have to make sure we put our multiplication in between. Okay. For third place, how many horses do I have to choose from now? Well, 2 of them already placed first and second. So 8 minus 2 is 6. And with this, we can go ahead and just multiply this out. Let's see, I don't know what that is. 8 times 7 is 56, and then 56 times 6 is 336. So we have 336 possible outcomes or possible trifectas, okay, for this particular problem. Okay, that's it. That's the counting principle. Not too bad. Here's where it gets interesting, okay? Counting with and without replacement. So if we take away options, that's why we had to go one down less. It said there was 8 horses in the beginning, now there's only 7, now there's only 6. But if we're not replacing it, we're leaving, I don't know how that would work with a trifecta horse race, but in different situations, if we're leaving everything in there, then the options for those numbers change as well. So here's how we're going to do this, okay? We're going to go right into an example, then I'll explain this again. It says how many 4-digit numbers can be formed from the digits 1 through 9 if no digit can be repeated. Okay, so this one is kind of like the one we did with the horses. We're going to first count how many numbers from 1 through 9. So from 1 through 9, there's a total of 9 choices. Okay, so we shouldn't have any number that's bigger than 9 for our the ones that we put in our list to multiply. Okay, so for our digit number 1, so it's a 4-digit number. So for our first digit, we have a total of 9 choices because, well, all of them are still there, okay? Then it says that no digit can be repeated. That means that for the second digit, so for the second number here, we can't whatever number we used here, we can't use it here. So now we have one less than that, which would be 8. Do you see how that works? For our third digit, well, again, they can't repeat. So whatever numbers we chose here, we can't use them here. So we're going to have to subtract them. So that's going to be 9 minus 2 is 7. Okay. And finally, for the fourth digit, again, we can't use these three. So we're going to have to subtract that number of possibilities from this one, which would be 6. And let me kind of show you what I did here. So here, let's use this one. We have the number of choices, okay? So the first one's 9 because, well, that's the first one. This one is 9 minus 1, which gave us 8, okay? This one is 9 minus 2, which gave us 7 because, again, we're counting back this way. And this one is 9 minus 3, which gave us 6. And in the end, all we do is we multiply these out. So 9 times 8 times 7 times 6. Let me write that nice over here. 9 times 8 times 7 times 6. Let's see what that gives us. 9 times, I'm using my calculator here. Times 7 times 6 equals, I'm getting 3,024. Okay, so this is the number of 4-digit combinations that we can find with the digits 1 through 9 if none of the digits are repeated. Okay, so this would be an example of without replacement, where you can't put that number back. So this one is without replacements, kind of like the horse example, okay? Now, what about this example where we have, let's go right there. How many 4-digit numbers can be formed from the digits 1 through 9? So same thing, if a digit can be used repeatedly. So in this one, even if we do get, let's say, I don't know, let's say we ended up with 1111, okay? That 1 can be repeated in all of those spots, okay? So with that in mind, for our first digit, well, we have 9 choices still, right? For our second number, well, it doesn't matter if it repeats, so we still have 9 choices. For our third number, again, it doesn't matter because we can repeat them, so we have 9 choices. And finally, for the fourth one, we have the 9 choices. So if we multiply these, 9 times 9 times 9 times 9, that's going to be 81 times 81. I'm just going to do it here. 9 times 9 times 9 times 9. That would be 6,561 possible outcomes. And this one would be, where did I put this? With or without. Oh, you know what? I did it backwards. This is without replacement. My bad, guys. I'm sorry. It's a good thing I caught that mistake before. You know, you want those extra 5 points. So this is without replacing the numbers. You put them back. Okay. This one is with replacements. Okay, but you get the idea. Okay. Remember, if you catch a mistake on my videos, let me know and I'll add 5 points to your assignments. Okay. All right. Let's go ahead and jump into another example here. We have, and this one's actually really similar to one of your problems. Okay, that's why I chose it on purpose. So we have, consider a Texas license plate with a 2-letter and 3 numbers combination. So for example, Texas dash 123. Okay, how many possible outcomes are there with the following parameters set in place? So let's look at the parameters, just means like conditions. Okay, so A, E, I, O, U are not allowed. So we can't use those. And then the number 0 is not allowed in the third spot. Okay, so let's kind of take a look at our options and let's see. For the letters, okay, we know that there are 26 letters in our alphabet, okay, but we can't use A, E, I, O, or U, which is 1, 2, 3, 4, 5. We can't use 5 of them, so we're going to have to subtract, which gives us 21 total for the letters. Okay, so that's our possible choices for the letters, okay? And then for the numbers, well, they're single digit numbers, 1, 2, 3. So for the single digits, we have 0 through 9. Okay, so for these, I'll just put here, for the numbers, it's 0 through 9, which is a total of 10 numbers. So 10 total, I guess you could say choices if you want. Okay, so 10. So keep that in mind, okay? And then it says the number 0 is not allowed in the third spot. So that when it comes to the third spot, we're going to have to keep that in mind. So here's how I would do this. I would kind of set this up for me. Oh, not like that. So let's do this. There we go. So this right here is your first letter. This is the second letter. This is the first number, second number, third number. And that's just my personal way. I'm just kind of setting something up here. Okay. So for the first letter, it looks like we have 21 options. We can do any of the letters except for A, E, I, or O, or U. Okay. For the second letter, it does not say anything about not repeating them. So we still have 21 options. Okay, we can repeat the letters if we wanted to. There's no restrictions about that. For the numbers, let's see, the number 0 is not allowed in the third spot. So for the first spot, we still have 10 options. Okay. And again, there's nothing about not being able to repeat the numbers. So for the second spot, we still have 10 options. Okay. For the third spot, we're not allowed to use 0. So that means I'm going to have to subtract 10 minus 1 because 0 is that one number, which would be 9. So this is the one that's going to be 9. And then we just multiply all this. So it looks like we would be multiplying, okay, 21 times 21 times 10 times 10 times 9. And I have no idea what that is. So let me see what that is. 21 times 21 times 10 times 10 times 9. I'm getting a huge number, 396,900. So if you wanted to get a license plate with this combination, you would have this many choices to choose from, 396,900. Okay, and that's it, guys. That's the gist of this video. It shouldn't be too difficult. As always, if you have any questions, go ahead and reach out and I'll help you out as best as I can, okay? Thanks.